Okay, so a couple of things that I wanted to review as well before I get to those worksheets. I showed you this in class, but I never actually reviewed splitting the middle term, guessing and checking. Hopefully we've done enough that we know how to guess and check, but on splitting the middle term, you kind of are looking for a way to split this up so that grouping will work. And to do that, you find two numbers that multiply to get whatever this A times C product is. So that A times C product is negative 24, 3 times negative 8. And find two numbers that multiply to get that, but add to get negative 10. So you've got like 1 and 24, 2 and 12, 3 and 8. 2 and 12 sounds good because they have a difference of 10. So since one has to be positive and one has to be negative, you want the 10 to be negative. So make the negative 12 times positive 2 gives you negative 24, and negative 12 plus 2 is negative 10. So I'm splitting this middle term up into these two. So it'll be 3x squared plus a 2x minus a 12x minus 8. And then you're grouping. So when you group the first two, you pull out an x, you're left with a 3x plus 2. When you pull out the second term, or group the second two, you pull out a negative 4, starts with a negative, so take out a negative, and that's going to leave you with 3x plus 2 when you divide both of those by negative 4. So we know grouping worked because these match. So now if I treat it like the two terms, they have a 3x plus 2 in common that I'll pull out in front, and then I'm left with x minus 4 as my other term. So I didn't review grouping because it involved, this one kind of used grouping. But just a review of that. Now, most people, you don't really need to do that on this one. You don't really need to do it on any, but on some it's easier. But if you were guessing and checking, you would just say, okay, what multiplies to give me 3x squared? And that's 3x times x. It's the only option. What multiplies to get 8? So you could try 1 and 8, or 8 and 1, 2 and 4, or 4 and 2. So we kind of already know it's 2 and 4. And then we would check 12x and 2x. Kind of gives us a 10. We got to play with our signs a little bit though, because we're supposed to multiply to get negative 8. So one of these is plus and one of these is minus. So if you just tried minus plus, and I purposely picked that to be wrong, you would check and you'd get positive 12x minus 2x, which would be positive 10x. We know that's not what we want. We want negative 10x. So if I switch those signs, now I get a negative 12x on the outer and a positive 2x on the inner. And negative 12x plus 2x makes negative 10x. Okay? Difference of perfect cubes, really quick, it's just a binomial times a trinomial. You just kind of have to know the rule. Cubed root of this is 2x. Cubed root of this is 1. If this is minus, this is minus. When you move over here, your first term is this one squared. Your middle term is these two multiplied together, but flip the sign, so plus 2x. And your last term is that squared, so it's always a positive. Sum of perfect cubes. Cubed root of this is 3x squared. Again, it's a binomial, trinomial. So 3x squared plus, because of the plus, and then y cubed. And then when you move over here, square this for the first term. Multiply them together for the middle. Switch the sign so it's a minus, and then it's 3x squared y cubed. And then y cubed squared is y to the 6th, and that's that. Difference of perfect squares. Now this one I purposely wrote doesn't start off as a difference of perfect squares, but there's a GCF. So I can factor out a 2, and that'll leave 100x squared minus 36y to the 6th. And this factors into conjugates. 10x plus 6y cubed, those are the square roots, and 10x minus 6y cubed with a 2 out in front. And then of course factoring by long division. Now if it's not factorable, if you tried to group this, it's not going to work. You're going to have x minus 7, and on this next one when you take out a negative 2, you're going to have a 7x minus 24. They don't match, so it's not factorable by your traditional methods. The only way to factor it is by long division. But remember, if you're factoring by long division, you have to have some heads up as to what to start with. So either they have to tell you a root, or they have to tell you a factor, or you have to use your calculator to find it. So if I type in this function, I can use my calculator to get me started. Take a peek at where the root is. There's one at -3. So also, I can obviously see the other two, but if they want to see it algebraically, they're going to want to see the long division. So if this root is -3, I can start by dividing out x plus 3. Now, for the record, someone else in the class might say, oh, well, 2 is a root. Okay, so they're going to start by dividing out x minus 2. Or someone else might see 1, 2, 3, 4, 5, 6, 7, 8. Someone else might see that 8 is a root, so they're going to start by factoring out x minus 8. At the end of the day, though, now, like seeing this, I do already know what my answer should be. I do need to show the work. There's your root, x plus 3. Then 1, 2, so at positive 2 makes a factor of x minus 2. And then we set it 8, so x minus 8. So this is how this is going to factor. I already know that. But I have to back it up with long division. The only one I'm stealing from the calculator is that one. And then I get this process started. So x squared, and then you'd multiply this by this. Do your subtraction. So that cancels. -7 minus 3 is -10. Repeat. X times what? -10x. Oops, not squared. Multiply it through. Do your subtraction. Be careful here because -14 minus -30 is -14 plus 30, which is 16. Bring down your 48, and you have x times what? 16. You get 16x plus 48. And of course, we have a remainder of 0, which we know should have happened because we already knew that this was a perfect factor from our calculator. So now, so far, we've taken this original problem, and we have factored it into this times this. So that's x plus 3 times x squared minus 10x plus 16. And now we can, our long division is done, we can take the rest of this and factor it by guessing and checking or splitting the middle term. So it has to be x and x. 16 could be 1 and 16, 2 and 8, 4 and 4. But knowing that I have a 10 in the middle, I'm going to try the 8 and 2. And it's a positive 16, so it's either plus plus or minus minus. So because the middle term is minus, I know it's that. And then we can just check our outer, -8x. Check your inner, -2x, you get -10x. And check your last, -2 times -8 is positive 16. And those are the three factors, and that's what we knew from the calculator we were aiming for. Lastly here, again, if we're solving by long division, this is taking the instructions, and rather than just saying factoring where we'd be done here, when it's solving, we're still going to factor by long division, but then we have to tee it up to find our solutions. So again here, if you try grouping, it's not going to work. So from this graph, we only see one answer, and I'm guessing that's 2, but second trace, look for your zeros, left bound, that's to the left, that's to the right, and so we have 2. So that is going to give us the first factor to divide out, x minus 2. Now what I do know just by looking at this is that the other two solutions clearly aren't real. There's no other intersection with the x-axis, so they're going to be imaginary, which is fine, we'll get there. So when we do this, x times x squared, do your subtraction, 5 minus -2 is 7x squared, bring down your 11x. Do your subtraction, 11 minus negative, so 11 plus 14 is 25. Uh-oh. Something went wrong. because that was supposed to go in evenly. I copied the problem down wrong. That wasn't a positive 5, it was a negative 5. So we got to go back. I knew something was wrong because I was about to get 25x minus 50 when I do my subtraction. I have a remainder. That can't happen. So there's your heads up that I did something wrong. I went back and found out that I had that as a plus. It should have been a minus. So negative 5x squared plus 2x squared is negative 3x squared. Changes the whole makeup here. This is negative 3x. Do your subtraction and get 5x minus 10. That's a 5x minus 10. Perfect. Okay. So now I have factored this into this, but remember we're solving, so this all equals 0. So now we would tee it up. We may try to factor that further, but it's not going to be factorable. Doesn't mean it's not solvable. Still tee it up. So this will give you x equals 2. And when you tee this one up, you'd have to solve your quadratic, and obviously by factoring is not going to work, so we have to do by formula. So the opposite of b, plus or minus the square root of b squared is 9, minus 4ac, all over 2 times your a is 2. So 3 plus or minus the square root of 9 minus 20 is negative 11, all over 2, which is 3. Plus or minus, the negative can't stay, so that's I root 11 over 2. So you have your 3 solutions, 1 real, and 2 imaginary that are coming in a pair of conjugates, which is normal. Alright, so from there I'm going to jump to this review note sheet that I made up, just to review all your parent graphs, transformations of functions. So, quadratic, critical points, 0, 0, 1, 1, and negative 1, negative 1, or negative 1, positive 1, rather. Those 3 critical points are all going to change with shifts and stretches and compressions, but that's the critical parent graph. So your domain is all your x values, negative infinity to infinity, and your range it goes as low as 0 to infinity, and it actually hits 0, so I'll use a bracket there. Okay, there are no asymptotes, and the only x-intercept on your parent graph is, I think that probably says x and y-intercept, so your x-intercept is 0, your y-intercept is 0. With a radical graph, looks like this. It's a dead end. You've got a critical point at 0, 0, 1, 1, 4, 2. If I plug in a 4, I'll get 2. Okay, the domain is only from 0 to infinity. If you look at the equation, I can plug in 0 and I can plug in positive numbers, but I can't plug in negative. That's why that domain is the way it is. And then the range, if you just look at it, it's just also from 0 to infinity. It'll go up forever. Okay, so that's because no matter what you plug in, the square root of anything is never a negative number anyway. There are no asymptotes here. The x-intercept is 0, the y-intercept is 0. Absolute value we haven't done too much of, but it does come up. It's a V-shaped. Your critical points are actually the same 3 critical points as your quadratic. It's just that the shape is a V instead of a U. So 0, 0, 1, 1, negative 1, 1. Again, domain and range are the same as the parabola was. And there we go. Whoops. No asymptotes again. Same x-intercept, y-intercept. Okay. Now exponential growth. Now this one happens to use a base of 2. Obviously the base can change. So it's 0, 1, and 1 comma b, which in this case is 1 comma 2. Okay. And you do have an asymptote here at the x-axis, which down here is the equation y equals 0. And then your domain is from negative infinity to positive infinity. You can plug in any x value you want. That's nothing there is going to cause an issue. But because your base is 2, you're never going to get a negative number, 2 to any power, even if you raise 2 to a negative power. Remember that raising 2 or any number to a negative power doesn't make a negative number, it makes a teeny tiny number because it becomes 1 over 2 to the 4th, which is 1 over 16, which is a small decimal. So we never get negative numbers, we never cross that on the parent graph, so our range is just from 0 to infinity, and that does not include 0 because we never touch the asymptote. So your x-intercept does not exist, and your y-intercept is 1. Now log base 2 of x, on the other hand, is the complete opposite because it's an inverse to the exponential. So we have the y-axis as our asymptote. We have not 0, 1, we have 1, 0, and not 1 comma b, but b comma 1, which is 2 in this case because your base is 2. So your domain, you can only plug in positive numbers. You can only take the log of positive. You see that? All your x's are greater than 0. So your domain is from 0 to infinity, not including 0. And your range, you can get anything from negative infinity to positive infinity. Your asymptote is the y-axis, which is equation x equals 0. And your intercepts, your x-intercept is 1. Your y-intercept does not exist. Everything flip-flops. Everything flip-flops because these are inverses. And lastly, the rational graph. It's kind of the one that comes in 2 parts. Okay, like this. You have 2 asymptotes, the x-axis and the y-axis. Your critical points are 1, 1, and negative 1, negative 1. Domain, you can plug in anything except for x is 0. You can see that there because you can't divide by 0. So domain is all reals except for 0. X can be any real number except x cannot equal 0. And your range, same thing. All real numbers except for you'll never have a y coordinate of 0. Asymptotes, you have 2 of them. And intercepts do not exist on the parent graph. Obviously, all of these things change once you start shifting, stretching, compressing, flipping, reflecting, all that stuff. So real quick, I'm just going to think about the transformations. Here's what, on an exponential parent graph of 2 to the x, my critical points were 0, 1, and 1, 2, stealing that from above. Now, the first thing that happens is a shift left 1. So when this moves left 1, this moves left 1. This moves left 1. There's my next set of points. Now when I stretch vertically by a factor of 3, this becomes vertically by 3. Anything vertical is going to affect your y-coordinate. Anything vertical, stretching by 3, is going to multiply that by 3. So there are your 2 new critical points. Oh, by the way, your asymptote that was here, when you shifted it left 1, it's still here. When you stretch it vertically by a factor of 3, it's still here because it's on the x-axis. And then when you shift down 4, your asymptote moves down 1, 2, 3, 4. So your new asymptote is going to be here. And these points, when you shift them down 4, that's vertical. That's going to affect this coordinate. It's going to go down by 4. This going down by 4 is going to be there. So our 2 new critical points are negative 1, and 0, 2. And nothing was flipped over, so it's still got that general shape. And that's the graph of that. Okay, on this rational parent graph, first thing, shifted right 3, which is going to take that vertical asymptote and shift it right 3. The horizontal asymptote getting shifted right 3 is still the same horizontal asymptote, so that's not moving. Okay, your critical points were 1, 1, and negative 1, negative 1. Let's see what happens to those when you shift them right 3. This becomes 4, 1. This becomes moving it right 3, add 3 to that. Right, negative 1, moved right 3 will become 2, negative 1. Left and right affects the x-coordinate. Up and down affects the y. So then we do have a negative, so that's a vertical flip. So that's going to affect your y-coordinate. It's going to flip it upside down, negate it. And then we have a vertical stretch by 2. So we're going to double our y coordinates. Double that, 2. So your new points are 1, 2, 3, 4, negative 2, and 2, 2. We can't cross those asymptotes. Okay, and then lastly, we have 3 critical points here to kind of track, no asymptotes. So first things first, horizontal compression by a half. So that's going to become 1/2 1. That's going to become negative 1/2 1, and 0, 0 is going to stay put. Then a vertical stretch by 3, 1/2 3, negative 1/2 3, 0, 0 is going to stay put. Then a shift up 1. So 1/2 4, negative 1/2 4, and 0, 1. This is my vertex, so it's still going to be my vertex, 0, 1. Then we're going to have 1/2, 1, 2, 3, 4, and negative 1/2, 1, 2, 3, 4. So this just became a much skinnier V shape. Got a couple more of these on the back. Your log parent graph. Again, your critical points are 1, 0, and B, 1, which is 2, 1. And we have an asymptote on the y-axis, which is going to move, so I'm not going to hit it. Or I'm not going to do it too dark. First transformation, horizontal flip, the negative. So this is going to become negative 1, 0. This is going to become negative 2, 1. Followed by a vertical compression by a half, which is not going to affect this one. But this one's going to become vertical compressed by a half, 1/2. By the way, when you flip horizontally the y-axis asymptote, it's still the y-axis. When you compress it by a half, still the y-axis. Only shifts really affect our asymptotes. And then shifting down 3, this shifted down 3 is still going to stay the same asymptote, so that's not moved at all. But this shifted down 3 will be negative 1, negative 3. And this shifted down 3 is going to be negative 2, negative 2.5. So negative 1, 2, 3, and negative 2, negative 2.5. So that is going to do this. This is a quadratic, so our critical points are 0, 0, 1, 1, negative 1, 1. We're going to first shift right 4. Add 4 to that, you'll get 3, 1. And then we're going to vertically flip, let's say next, so 4, 0 is going to stay. This will become 5, negative 1. This will become 3, negative 1, and then stretch vertically by 2. So that's why that's not going to touch that. Vertically by 2 is going to make this negative 2. Vertically times that by 2 is going to make that negative 2. So your points are 4, 0. 1, 2, 3, 4, 5, negative 2. And 3, negative 2. And a couple things that we can kind of think about with quadratics, because we know them a little bit more in depth, is that there's a negative a value. So that got flipped upside down. Remember your HK vertex format. Your vertex is 4, 0. 4, 0. So a couple things there you can relate to what you also know about quadratics. And then your radical function. So our parent graph looked like this. We had 0, 0, and 1, 1. And 0, 0 was kind of the dead end. So whatever this morphs into will also be the dead end. First things first, we've got a horizontal flip, which keeps that the same, but this becomes negative 1, 1. Then stretch vertically by 3. That's going to stay the same. This stretched by 3 is going to multiply it by 3. Remember, stretches are multipliers. And then shifts, add and subtract. So shift up 2, which will make this 0, 2, and we'll make this negative 1, 5. So we have 0, 2, that's our dead end, and negative 1, 1, 2, 3, 4, 5. And this kind of has the same shape, but it's headed off to the left. Parent graph heads off to the right, but because we had a horizontal flip in there, right there, it now heads off to the left. And it's a little steeper on top of it because of this vertical stretch. Okay? The three functions with limited domains. You see your domains are limited for radicals, logs, and rationals. Radicals, logs, and rationals. Radicals, you can only take the square roots of non-negatives, meaning this number can't be negative, so it has to be greater than or equal to 0. Add 3 to both sides, that's going to give you your domain. Done. So your domain would be 3 to infinity. Here, you can only take the logs of positives, so this needs to remain positive. So add 7, x has to be greater than 7, so this one's domain is 7 to infinity. And lastly, you can't have a 0 in the denominator. So if you factor this, it's easier to see that your excluded values are that x cannot equal -3 and x cannot equal 3. X can be anything else, but it can't be those. Because if it is, you'd be doing 2 divided by 0, and that's a problem. Okay? Transformations here. The first transformation, this is just a generic graph. It's not really a family of functions we study, but this shifts right 3. So every point is going to shift right 3 to start. So 1, 2, 3. This one goes 1, 2, 3. This one goes 1, 2, 3. So far we're here. This is 0. 0 goes 1, 2, 3. This one goes 1, 2, 3. And this one goes 1, 2, 3. So there we are, shifted right 3. Then it's vertically flipped. So this that's 1, 2, 3 below is now going to be 1, 2, 3 above. This one's at 1 below, it's going to be 1 above. This one's 2 below, it's going to be 2 above. This one's right here is going to stay. This one's 4 above is going to go 1, 2, 3, 4 below. And this one's 1 above is going to go 1 below. So we have that look, which means we can kind of get rid of that intermediate one. That's after our flip. And then our vertical compression by 1/2, this that's up 3 is now going to only be up 1 1/2. This that's up 1 is only going to be up 1 1/2. This that's above by 2 is only going to be above by 1. This one is going to stay right there. So far we've condensed it to this. This one that's 4 below is only going to be 2 below. So it's going to, this one that's 1 below is only going to be 1/2 below. And so that all these points got smushed down towards the x-axis. All these points got smushed up towards the x-axis, and that's what a vertical compression does. So if I get rid of that intermediate graph, I have those points. Now, the other way to do this would be kind of the way we did our parent graphs. If you don't want those 5 graphs kind of on top of each other, you could start by taking all of these critical points. -1, 2, 3, 4, 5. -5, -3 is one. -3, -1 is one of them. -2, -2. 0, 0. 1, 2, 3, 4, 1, 2, 3, 4, 4. And 5, 1. And you can kind of go through each point and handle all these transformations. Right 3, that's moving right 3, so it'll be -2, -3. This one's going to be 0, -1. This one's going to be 1, -2. I'm adding 3 onto all of these x coordinates. This will be 7, 4. This will be 8, 1. That shifted everything right 3. That's that. Flip everything vertically. That's going to negate all of your y coordinates. So the -3 is going to flip up to a +3. The -1 is going to flip up to a +1. The -2 is going to flip up to a +2. Then 3, 0. Then 7, 4 is going to flip to a -4. 8, 1 is going to flip to 8, -1. And then lastly, the y coordinate gets compressed by 1/2. So 3 cut in half is 1.5. 1 cut in half is 0.5. 2 cut in half is 1. 0 rather cut in half is still 0. -4 cut in half is -2. -1 cut in half is -0.5. So you'd see that that's where all our points are. -2, 1.5, 0.5, 1, 1, 3, 0, 7, -2, 8, -0.5. So some people might like to go point by point, then they only have one graph to do at the end. Others might like to slowly move the graph just to see it all visually unfold. So that is that. I'm not going to do the homework with it, it's just more practice on the same.